There's been a lot of confusion about phase velocity. This tutorial is based on papers published in scientific journals, which are summarized in my channel on YouTube, and all of these are listed on my webpage. This tutorial takes 4 steps: classical mechanics, momentum as mass times velocity, kinetic energy is half mv squared. Secondly, classical wave phase velocity. Waves are everywhere because it's easier to make waves than to push a barge. And the phase velocity is the wavelength multiplied the number of cycles per second. And that's equal to the ratio of the angular frequency divided by the wave number or wave vector. This is simply by definition. There's nothing to understand. Thirdly, we have to take into account relativity. Einstein's E equals mc squared relativistic mass divides into rest mass plus momentum. And the rest mass itself, after quantization, also divides into quanta. The energy is proportional not so much to the intensity of the beam as to the frequency of the interaction. Likewise, the momentum is proportional to the wave vector. Substituting these values into relativity, we find omega squared is equal to k squared plus mass squared using natural units. And we can differentiate this and find that omega over k multiplied by the derivative d omega by dk is equal to a constant c squared. What is omega over k? We saw that before. It's the phase velocity. And what is d omega by dk? Well, that's what we'll see in the next slide. But just remember that c squared over vp equals what? Before we go on, think of mass. Mass is equal to omega squared minus k squared. It separates into 2 parts, a wave part and a particle part. But we won't say anything more about that today. Now, how do we go on? We'll study classical energies first and then move on to relativistic energies. Well, rest energy is equal to rest mass times c squared. And the energy is the rest mass plus the kinetic energy, half mv squared. This value is given by the binomial theorem from the proper value. And what is momentum? mv. Substitute for m, and we get E0 over c squared. Rearrange, and we find the group velocity is equal to p c squared over E0. And how do we go on from there? Well, when we move from the low energy range to the high energy range, remember the mass increases, the energy increases, but the speed stays the same. So what happens is we have to substitute for E0 the relativistic energy, and then we find from this formula, substituting for P and E, the group velocity is k over omega times c squared, which is equal to c squared over the phase velocity, which is equal to d omega by dk in natural units, where c squared equals 1. We can plot those values, but we'll do that in a moment. But first notice the group velocity is the inverse of the phase velocity. De Broglie's momentum depends on the group velocity, d omega by dk, where Planck's law depends on the energy, which depends on the phase velocity. That is omega divided by k. Well, here they are. Here's a wave group. There's a phase and a group, and the group velocity in a massive particle is different from the phase velocity. Light is different. Light is massless. The group velocity is equal to the phase velocity. Notice another thing on this wave group. The uncertainty is the full width half maximum. And it turns out, I've shown this in other work, that the quanta that we've discussed are the result of resonances at emission, scattering, or measurement. But once again, that's a problem for another day. I can illustrate what we've been talking about. Here's rest mass, here's relativistic mass, plotted against wave vector k. And here's the group velocity, half mv squared. It is classical at low energy and tends to see into relativity, as Einstein pointed out. The photon has energy to momentum ratio 1:1. Energy is equal to momentum because it's massless. The phase velocity is the inverse of the group velocity. Other features of this formula I've described elsewhere. Well, how do we derive group velocity and phase velocity? This is theoretical. This is experimental. You can get these numbers from electron microscope handbooks. Here's the rest mass. The energy is the rest mass plus the energy of the gun, and the momentum is the difference in these two vectors. Here they are. Frequency, wavelength. The product is the phase velocity. The inverse is the group velocity. The product is the constant c squared. The ratio is 1 at high C, relativistic, but gets very large at low energy. These plots are logarithmic, as you can see. Well, let's go on to Minkowski space, and this is the last slide, except for the conclusions. In Minkowski space, which is relativistic, time in the vertical direction, propagation direction in the horizontal direction, and the transverse plane, YZ, supposedly, in this case, uniform, is used to describe velocities in Minkowski space. These light cones define where a second particle has to be in order to interact with the particle at the origin. If the second particle is outside the cone, there's no interaction. But if the second particle is inside the cone, they are electromagnetically correct in the future or in the past. That's Minkowski space. The blue line is an electron in the Stanford linear accelerator, going at half the speed of light. It travels half the distance in a given time. And what about the phase velocity? It travels double the distance in a given time. And can we experience the phase velocity? The phase velocity is described in this formula. The phase velocity was omega over k. And the group velocity, as you remember, was d omega by dk, which is given to us by the theory of relativity. The phase velocity is out in the tail, down here. A phase separated from a wave group on the upper cone is so small that it doesn't interact. What does interact is the uncertainty within the wave group, this uncertainty. We'll be able to use that to make a few conclusions. Electromagnetic interaction needs 2 electrons inside the Minkowski cones. Coulomb interaction needs 2 electrons inside the blue cone. And entanglement needs 2 electrons inside the green phase cones. which are not drawn in this diagram, but which you can extend mentally. Finally, the infinite wave of a particle locates at the center of the enveloping mass. Phase is uncertain beyond the center and is limited by it. Internal motion is faster than the group and transfers this extra freedom in intrinsic spin, superconductivity, and Messier effect. Entangled needs 2 electrons inside the phase codes.